Okay, welcome to Lesson 7 in our continuing study of ratios and proportional relationships. Lesson 7 is the beginning of what we consider Topic B. Okay, we just finished Topic A, which was proportional relationships. Now we are talking about unit rate as the constant of proportionality. Okay, so we're going to see how this constant that we've been talking about is related, or actually is identical, synonymous with unit rate. Okay, so this first problem that you see there in your binder concerning the National Forest deer population is a bit messy because I'm going to show you there's a few typos in here. There is a second generation of these student materials that we will be using when we start Module 2, which won't be for quite a few lessons yet, but they have been cleaned up quite a bit. So you'll notice, let's read this together. So wildlife conservationists are concerned that the deer population might not be constant across the national forest. Okay. The scientists found that there were 144 deer in a 16 square mile area of the forest. Another part of the forest, conservationists counted 117 deer in 13 square miles. Yet a third conservationist counted 24 deer in a 216 square acre plot of forest. Now you can see what's wrong with that right there, that last value. And again, it's not that there should be anything wrong with it. I mean, this could indeed be the case, but as they go and as they what they're trying to keep this as a similar unit rate. That's the whole idea here. First of all, they have the wrong unit here. They had square acre. It should be square mile. If you want to make this change in your book, you can in your binder. And also they have these numbers mixed up. It should actually be 216 deer in a 24 square mile part of the forest. Okay. So anyway, those are the numbers we'll use. Really doesn't quite matter because we're just going to be just looking at proportions. I don't want to sound insensitive, but question A, not real interested in that right now. I am an animal lover for sure, and there are many reasons why the deer population not being constant in a certain area is important. It might mean many things. If there's overpopulation, there might need to be some culling of deer as they eat resources and kind of starve themselves out. Yeah, so again, it could be many reasons, but this could be whatever you might think, you might imagine. But more importantly, what I'd like you to be able to do is to immediately create a table. Okay, so if we're looking at the population density, okay, of deer per square mile, we need to start with a table. Okay, so if we go ahead and make a table, and if you want to go ahead and just make a table along with me. Okay, you guys have gotten pretty good at this, I've noticed. So first here we have square miles. Okay, and we have number of deer. Okay, and then we have what's considered our population density. Real important study and very useful use of ratio. Okay, we have three different scenarios. We have a 16 square mile area with 144 deer populating it. We have a 13 square mile area with 117 deer, and then, like I said, these numbers were wrong in the problem, so it should be 24 square miles and 216 deer. Okay, So what I'd like you to do, now if we were to look at this in terms of x's and y's, which we want to really start doing more so, we're going to look at this column in our table as x and this column as y. And this is a good habit to get into, and you'll see in later lessons, but look at that left x and then the right y. Now the way you would then put, you would write your population density. You want to know how many deer per square mile. So we're looking for deer per square mile, or mile squared, okay, per square mile. So in that sense, you know you would have to put the deer on top as your numerator per square mile, so over 16. And you can see that what a table like this is actually looking at or comparing is it's using y as a function of x. Okay, so you're going to see that your y value is going to be your numerator, while your x value is going to be your denominator. Okay, so good to get used to that, setting your table up just like this and knowing that you're looking at y as a function of x. And again, that's going to come into play, if not this year, next year for sure. So I'd like you to go ahead and just pause the presentation and figure these out. Figure out the population density, number of deer per square mile in all three of these cases. Okay, so over here, I don't want fractions as your answers right now. Okay, I just gave you this fraction just to show you where to start. Of course, you want to make create a whole number or a mixed number out of that. Okay, so come back after you've done that. Okay, so hopefully we all did our math correctly and set up our y as a function of x. So here was our x again, here is our y, and so y as a function of x, of course, was 144 divided by 16, and you would have gotten 9. So if we had 9 deer per square mile, okay, so 9 deer per square mile, this is going to be the same. Per square mile, mile squared, and then this was the same as well. Okay, so if you did get that, congratulations. And yeah, what can we tell here? We can tell, if I were to ask you, actually let me ask you, do we see a proportional relationship here? Do we have a constant of proportionality in this table or in this section of some part of the national forest? And the answer would be yes, because as you can see in all of these sections we have a 9 deer per square mile. Now that per square mile is called something else, hopefully you know, and that would be the unit rate. Okay, unit rate, and we can see it right down here. This question right here is asking us to fill this in. The unit rate of deer per 1 square mile is, and that would be 9. Okay, so we have 9. Okay, and the way we know this relationship is proportional is because they are 9 deer per square mile in each of these scenarios. This one, and this one. Okay. Now this whole constant, of course, is called the constant of proportionality, which is related to unit rate. Okay, so these constant of proportionality is indeed synonymous with unit rate. Okay, so these are the same thing. Okay, the constant of proportionality is going to become more important when we talk about that relationship between x and y. Okay, x and y. We'll talk about that relationship again as y as a function of x. Okay, so moving further down on your paper, we've already identified the unit rate of deer per 1 square mile as 9. Okay, now constant of proportionality, if we were going to make an equation out of it, we would say k. Now k is going to be our symbol for this idea of constant of proportionality, and in this case the k equals 9. Okay, so these constant of proportionality is synonymous with k, and unit rate, as you can see, is the same as this constant of proportionality. Okay, now the meaning of constant of proportionality in this problem is that there are 9 deer for every 1 square mile of forest. Okay, so we could write down, let's go ahead, let me do this. Why don't you go ahead and I want you to use this unit rate, okay, to calculate. Okay, well let's determine. Just actually have to give us to you. Determine how many deer there are for every 207 square miles. Okay, so you're going to take a 207 square mile swath of forest and tell me how many deer, based on this unit rate, there would be in that area. So go ahead and pause and do some calculations and come on back. Okay, so if we were going to use the unit rate to determine how many deer in a 207 square mile area, we can just go back and we can look at our original table of data. Now we are actually going to be working in the area of x. Okay, so what we're doing is we're actually working with a formula that looks like this. So here's our k, and that's our k, our constant of proportionality. Okay, actually let's do this first. Let's go ahead and let's look at it. Let's look at our x. So we have our x. Okay, our x times our k, which is our constant of proportionality, is going to be equal to our y. Okay, and if we do that over here, we can see that our x for the first column is 16. 16 times 9 equals 144. Okay, and you can see. So this right here is what we're working with. We're working of x of k. Okay, or k of x is going to equal our y. Okay, so let's go ahead and let's plug in the numbers we have right now. We have a number now we want to plug in for x is 207. So we have 207. Our k is 9. Okay, so this is our x, this is our k, and now we're going to get our y. All we have to do is multiply. And if we multiply 9 times 207, we get 1,863. Okay, so 1,863 would be our answer for this question right here. 1,863. Okay, now we can turn the tables a little bit here, and we could actually, let's go ahead and ask, how about let's do another one. Use the unit rate, the same unit rate, okay, which we know is 9. Again, the constant of proportionality is 9. Use the unit rate to determine the number of square miles in which you would find 486 deer. Okay, so go ahead and use these numbers, use the constant of proportionality, and figure this this problem out. And I'll just pause it for a bit. Okay, so if we apply our formula again, our x times k equals y, and just plug in these numbers that we have, our y is actually our number of deer. So we have the y already. Kind of working backwards here, we have our constant of proportionality, or our unit rate. What we don't have is our x. Okay, we don't have our square miles. And again, let's just go ahead and take a look at that original chart. You saw our square miles right here is our x. Okay, so let's go back. And no, right there. Oh, no, right there. Okay, so now just a real quick tip if you're working with multiplication and division. When you're working this way, as you can see, this is multiplied. We're multiplying these numbers here. Okay, we're multiplying that way because we're multiplying x times k to equal that. Now, if I'm going to work this way, we know that division is the inverse operation of multiplication, which means it's the opposite. Okay, so if I am multiplying this way, I divide this way. Okay, so then all we'd have to do is take 486 and divide that by 9. Hopefully you guys did that. And if you had done that, you would have come up with the answer of 54. Okay, so so those are that's the number of square miles. Actually, yes, hold on a second. Is that right? That is right. Number of square miles we would find, in which we would find 486 deer. Okay? Alrighty. Okay, so let's go over a little bit of vocabulary here. This is on that page right below those two problems we just did in your binder. So this idea of constant specifies a unique number. Okay, this idea of a unique number. A variable, okay, is a letter that represents a number. Of course, we're talking about x and y and k. So I'm reading here, if a proportional relationship is described by the set of ordered pairs that satisfies the equation y equals k times x, where k is a positive constant, then k is called the constant of proportionality. Okay, and that's what we talked about before. It is the value that describes the multiplicative relationship between two quantities. And we talked about this idea, we talk about ratios, this idea of a multiplicative relationship. Okay, that word I had a little trouble with. Some of you recall in those intro videos. Yes, between two quantities x and y. The xy pairs represent all the pairs of values that make the equation true. So you could have numerous xy pairs that would make an equation true, okay, based on having this constant of proportionality. Okay, and here's a note here. In a given situation, it would be reasonable to assign any variable as a placeholder for the given quantities. For example, a set of ordered pairs TD would be all the points that satisfy the equation D equals RT. Okay, and now this D equals RT will become very familiar to you if it isn't already, and that is actually the distance equals rate times time. Okay, and that's when we find miles per hour and such like that. So yeah, that's your distance time ratio there, that rate. So where r is positive constant, okay, and you see right there r is a positive constant because it is a rate, okay, or the constant of proportionality. This value for r specifies a unique number for a given situation. Okay, so if you're going 60 miles per hour and you know how far you went, you can tell how long it was going to take you. Okay, some things I've written down here, and hopefully you guys are taking notes right in your binder. There's quite a bit of space on the bottom of this page, but I'd like you to write some of this down, and if you need to, just go ahead and pause and take time to write it down. But unit rate and constant of proportionality, they are the same. Okay, they're the same thing. They represent the same number, the same value. Okay, they both represent the value of the ratio y to x. Okay, so very important, y to x. Okay, y to x is very different than x to y, as many of you have found out when we did the growing dogs problem. Just flipping those y and x values means all the difference in the world. Many of you had Sally as having grown more, and Sandy having grown more, because you had put her ending or beginning weight, the 7, over her growth, the 4. But when it should have been flipped, it would have been 4 over the 7. And you can see, if I just wrote that down here, how different 7 over 4 is than 4 over 7. Here we have nearly 2. If we were going to put that into a whole number, and then we have less than actually a little bit more than a half. Okay, so I don't want to confuse you with that. But if you do remember, those of you who did that and got that wrong for that reason, what I'm trying to stress is the importance of writing your ratio or your fraction, which is also a ratio, correctly. Okay. Okay, we have 2 more examples in your binder that I would like you to do. I'll go ahead and read the problem right now, and you can go ahead and fill out answer A and B, similar to what we did in example 1. And if you would pause while you do that, and then come back and I'll go over the problem with you. Okay. So Brandon came home from school and informed his mother that he had volunteered to make cookies for his entire grade level. He needed 3 cookies for each of the 96 students in 7th grade. Unfortunately, he needed the cookies for an event at school on the very next day. Brandon and his mother determined that they can fit 36 cookies on 2 cookie sheets. So, A, is the number of cookies proportional to the number of sheets used in baking? Create a table that shows data for the number of sheets needed for the total number of cookies needed. Okay, so again, pause, read it over. Always highly recommend students read a problem over, decide what they exactly are looking for. Create your table. If you create your table correctly, it'll really open up a world of solutions to you. Okay, so go ahead and do that. Read it over again. Create your table and answer those questions. Come on back and we'll go over it together. Okay, so the first thing you'd probably want to look at here in this problem is this idea of how many cookies he needed. So he needed 3 cookies for each of the 96 students in 7th grade. So that's going to require a little bit of multiplication. So hopefully you guys understood that. I'll tell you honestly, though, I'm looking at this problem. It's a little bit convoluted in the way it's written. I have to tell you. I think I'm going to just ask you guys. That's 288. So he needs 288 cookies. But now this part right here, Brandon and his mother determined that they can fit 36 cookies on 2 cookie sheets. So why don't they just say 18 cookies in 1 cookie sheet? Right? So the idea is that these guys are, oops, I lost my, ooh,